Physics, about to interview Professor Dennis Whyte. He's the Hitachi American Professor of Engineering at MIT, a professor in the MIT Department of Nuclear Science and Engineering, and the director at the MIT Plasma Science and Fusion Center. He's the winner of numerous accolades, including in 2018 the Fusion Power Associates Board Directors Leadership Award, which is given annually to individuals who've shown outstanding leadership qualities in accelerating the development of fusion. This leadership extends to heading up the fusion project SPARC, a compact high-field fusion energy device in collaboration with MIT-born private fusion startup Commonwealth Fusion Systems. I was lucky enough to listen to him speak yesterday at Fusion 22 and learn more about some of the extraordinary strides him and his team are making towards turning commercial fusion energy into a reality. It's a really dynamic field, and I hope you enjoy the conversation. So, welcome, Professor Whyte. Thank you for joining me here today. Yesterday in the conference, you mentioned that SpaceX blocked Commonwealth Fusion Systems' website since you were taking too many employees. Suppose, however, that I'm a potential future employee that hasn't been convinced yet of going down the fusion route. Why should I pursue this rather than some other energy technology such as photovoltaics?
Oh, that's a very good starting question. No, I mean, it has to do with what you're interested in terms of science as well too. So I'll start with the fact that fusion is so extraordinarily multidisciplinary, people tend to think of it as having perhaps plasma physics, because plasma is the originating phase of matter, perhaps nuclear physics as well too. But really, an engineering system, a fusion engineering system, has almost every discipline of engineering in it, and many of the sciences in it as well too, including physics and chemistry, because that's usually what it takes to deliver totally new energy sources. So, I made the decision to enter into this field like a long time ago, like 30 years ago, and I never regretted it because it never got boring, that's for sure. There was always some new topics to look at, and I've been blessed by being able to have an extremely diverse career about doing the things that I've gotten to know: plasma physics, atomic physics, material engineering, chemical engineering, just to name a few. And then in the end, it's sort of the impact. I mean, as scientists, as scientifically curious people, we want to pursue things which are new knowledge, but we also want them to have impact. It's hard to argue that there's things that look like fusion around very much, like photovoltaics is very, and there's actually still advances being made as well too, but it's an established industry, and that there's still improvements to be made, but they're more marginal, right? Or they're more incremental. In fusion, there are major innovations to be had, and so that's one of the reasons to go into fusion. Finally, and fusion itself, as I explained in the lecture yesterday, is sort of extraordinary in the sense that the physical conditions at which you can make fusion energy vary by factors of like 10 billion. Again, it's hard to get bored in fusion, right? But also then the impact of fusion is extraordinary, mostly because it'll be almost an infinite impact because it has had zero impact so far. Exactly, it's all in the denominator, right? Yes, yeah.
So thinking back to when you were a student yourself, did your reasons for going into this kind of line up with that?
I mean, for myself, it was also decisions about whether or not, when I finished my undergraduate degree, many of my colleagues were going into, interesting, I had a degree in engineering physics, which is a sort of applied physics or mixture of physics and engineering disciplines. And many of my colleagues went into finance, where they did very well. Some other ones went into business. Very few went into research. And at that point, undergraduates were not allowed to do research, because we were going to break something, in the laboratory. And I stepped into a research lab, and within like a few weeks, it was like, oh, I know I'm probably going to be doing this the rest of my life. I just didn't actually know it was going to be, grow to this thing that we're doing right now. But it's another part that I always tell students, right, is that don't try to force yourself too much into a particular situation. Find out what really motivates you and what fulfills you as a student of life, in some sense, right? It's a little corny, but that's actually what you should be. That's what you should be doing, and that reflects my own my own experience was that, the idea that you're doing, in fact, my daughter recently got this experience. She's been doing research and kind of got the research bug is what I would call it, right? Is, you're going along and you work really hard and then you're looking at something and you realize like no other human being has ever like had that particular insight as to what you are doing. And it's sort of quite thrilling. Yeah. And but then I think combining it with something that you feel actually is going to be, I mean, there are many scientific disciplines where you do it purely for that drive, and that's absolutely great as well too. In something like fusion and energy, you want both. You can have it both ways, I would say. You can have the discovery, but you can also have the potential societal impact, which I think is very important actually as well too. That wasn't. It was a bit of my motivation, but honestly, fusion still seemed like more of a. It was still driven as a scientific curiosity, and had less. It was very less unclear about what the pathway would be to impact, and now it's more clear. Yeah.
In those first few weeks, what sorts of things were you doing then that got you?
Oh my gosh, it was everything. It's like I couldn't stop. It's like I didn't get into the lab, so it was like, well, so we start running a spectrometer, which is essentially a tool that tells you about the makeup of the light that you're looking at. And we started to do that. I started to work on a computer program to like analyze it. Computers are a lot different than they are now, and it's just sort of that sort of thing of being able to sort of follow your curiosity it's like, wow, that's a great kind of job. And then this translates into more things, into postdocs and into research scientist positions. There's not many jobs in our society where you're encouraged to follow your curiosity. That's pretty unique.
So just before we go any further, for anyone in the audience who might not know, could you just briefly outline what nuclear fusion is and the main approaches there are at the moment to try to harness this process for energy?
So this is for students, and I'm assuming they're mostly interested in STEM, so I'm going to be a little bit more technical. Okay, so fusion is the process in which you combine light elements, and the reacting products that come out on the other end have lower rest mass. And the reason for this is because what you're doing is you're rearranging the strong nuclear forces, which are part of nuclei, right? And the most common aspect of this is you combine hydrogenic elements, so hydrogen, deuterium, tritium. Hydrogen is the process in the stars that works, including in our own sun, and this results in helium, which has an extremely stable nucleus, and therefore it has a lower rest mass. So the deficit in mass that you get from the beginning products to the end products are converted into kinetic energy by E equals mc squared. But because you're rearranging nuclei have factors of what is it? It's 4,000 times higher mass than electrons. This is one of the interesting features of atoms, of course, right? Is that almost all of the mass is in the nucleus, but it contains almost none of the volume of an atom. So why is this important? Well, it's because atomic processes, which we would call chemistry, rearrange electrons. By the way, it's an interesting question actually to you, if your audience are scientific curiosity. Where does energy come from when you burn fossil fuels? It also comes from E equals mc squared, because all energy comes from that. In fact, energy and mass are just simply equivalent to each other. So that energy comes because that you're rearranging the very, very minute changes in the rest mass of molecules and atoms. That's basically the electrons. Nuclei are just in a totally different realm because they're so much smaller and they have so much more potential energy in them. When you rearrange them, to first order, you're releasing tens to 20 millions times more energy per unit particle than you can ever get from a chemical reaction. And there's basically nothing in between because this is the nature of atoms, right? So that's the origin of fission energy, which is the splitting apart of the most unstable nucleus. And that gives you extraordinary large amounts of power per unit mass. But fusion is literally the opposite of that. Like it combines stable elements into even more stable elements, and then releases large amounts of energy. So to make this, so we've known about this for a very long time. Since we were able to trigger the first artificial nuclear reactions using accelerators, actually not too far from here. In fact, in Rutherford's lab, Cockcroft and Walton basically demonstrated the first controlled man-made nuclear reactions where it came from these processes, that we knew this was and we knew, then we figured out how stars worked as well too, and we realized this could be a potential energy source, and that's what we've been pursuing, because the conditions that are needed to actually, so we've made the fusion reactions for a long time, we've actually triggered fusion reactions for a long time, but making net energy from fusion requires, well, something that's more like a star, because it actually has to have high average temperature to basically get over the hurdle of making it a net energy source.
So that leads us nicely into talking about the work you do in the SPARC project in collaboration with Commonwealth Fusion Systems. I know that you've had some truly remarkable successes so far. Could you speak to some of these successes and the importance of these successes in developing commercial fusion technology?
So so there's many ways, it turns out, to actually reach these conditions necessary to make fusion energy, right? And what this requires is fusion energy gain. So what does this mean? So again, I told you we can make fusion reactions all day long in my accelerator laboratory, but this will never exceed a gain of and what I mean by gain is that the amount of energy it takes to run the accelerator is that the amount of fusion energy that I get out is always like a fraction of a thousandth of actually what that is. So it can't be an energy source. So in these other configurations, and particularly magnetic configurations, which are the leading configurations, it's the idea you replace the gravitational force in the sun with a magnetic force, which is the containment system. So this is why is this required? Because it has to achieve temperatures, not energies, temperatures, which exceed 50 million degrees Celsius. This cannot work in a physical container on Earth. It works in the sun because the center of the star gets hot, but it can't escape because of its own gravity. So in these configurations, which we call tokamak, which is a weird sounding name that basically means a magnetic chamber built as a toroid or the shape of a donut, these configurations have been able to hold the plasma fuel at these conditions, in fact, exceeding the temperature of the center of the sun, and getting right up to the point where, in fact, the system is very, very hot, but it doesn't have quite enough density and confinement of the fuel to actually push it over the point where the fusion reactions are so plentiful that they're actually the dominant means of keeping this medium hot to, in fact, make more fusion reactions. And of course, this is that's the key threshold to get over for fusion as an energy source on Earth. So go back to those particular examples. There's many of these configurations called tokamaks, magnetic chambers that hold this star in place around the world. JET had some, which is the one here in the UK, had very exciting successes. Has been operating for many decades, and recently actually set a new record for the amount of energy made by fusion reactions. But it wasn't quite yet up to a net energy gain of 1. So that was very exciting, 60 megajoules of fusion energy. So, this is on the order of 10 million watts of power, over 5 seconds. I mean, this shows, in fact, that what sounds like science fiction of holding something at 100 million degrees and making fusion reactions is possible. SPARC is our own take on this, which is allowed by the advent of new technology that allows us to make much stronger magnetic fields, and therefore the containment force gets more effective. And in fact, very much inspired by JET, it's a very international collaborative effort. We have taken a look, in fact, at the JET parameters and the conditions which they achieved, and then if you add in a stronger magnetic field, it turns out that we should be able to get to an energy gain well past 1. And that's going to be extremely exciting. And we're building that project right now.
And one of the key successes being this much stronger magnet. Could you maybe speak a little on that?
Yeah, so in the end, the way that you make this magnetic cage is you have to make very strong magnetic fields, and you have to arrange them in a particular configuration. So most people are familiar with magnets of like this, the magnets that you put on your fridge. This is a permanent magnet. So those don't have strong enough magnetic field and therefore force, nor do they have the right topology of the magnetic field. So we use electromagnets, which is a fancy sounding name, except this is basically, it's pretty simple conceptually. It's essentially a ring that contains an electrical conductor, and you pass electric current through this ring many, many times, and this produces a magnetic field that goes through it. The one that you might, if you probably have these, I'm sure you have these in the UK, like wrecking yards, right? You see that great big thing that comes down and picks up the car, right? That's an electromagnet, because it can be turned off and on by turning off and on the electric current. But in fusion, you need a special kind of electromagnet. It must be superconducting. And the reason for this is that if you pass the electric current through a normal conductor, this will consume staggering amounts of power because there's resistance to the current. A superconductor has no resistance. And therefore, you can put this current in, it will not dissipate, and it will not use electrical energy to maintain the magnetic cage. So on that one, most people are familiar with the superconducting magnet. This is what is an MRI, right? The medical imaging technology. This large thing that your body goes through is a large superconducting magnet that stays energized for years without consuming electricity. It just needs to stay cold. So this then goes to so superconductors are necessary to make an engineering plant net positive in terms of energy. Otherwise, you'd use too much electricity keeping the magnetic cage going. But superconductors also have this will not become a lecture in superconductors. You can go look it up. But they're basically they're realized by quantum physics in the end about the state of nature that allows the electrons to basically go on these conduction paths without dissipation. And one of the features of this state of matter is that it only has a certain tolerance to magnetic fields. And the magnetic field is literally the force which is being exerted on this fuel to keep it in place. So what our team realized is that we picked up on a new superconducting technology that came along. It had been commercialized sort of in about the middle of the last decade. And we realized the potential, in fact, for fusion electromagnets. Started the company, Commonwealth Fusion Systems, and then MIT, where I'm the director of the lab there, and our own spin out. We basically took this rather new technology, 30 patent disclosures later, and we built a completely new kind of technology that could access much stronger magnetic fields, but in a superconducting magnet, which means that it's now feasible to use in energy systems. And that's the basis of SPARC, which is the tokamak that we're building.
That's really cool. Okay. So having spoken about that challenge that's been overcome, what are some of the challenges that there are remaining that young people can get excited about potentially working on?
So really, the next threshold is in fact this achieving net energy gain. So what does this mean? So again, recall, this means it's the amount of fusion power that's being produced by the reactions of this fuel exceed the amount of power that you're applying to this medium, this plasma, which is what it's in, to keep it hot, right? And so all conditions, so we've succeeded in exceeding 100 million degrees, but we've done this in a way that and we've made fusion reactions, but we're applying much more, significantly more heat, like 3 times more external heat than the amount of fusion power that we're receiving. So why is this such a big threshold? Well, it turns out in the leading and most dominant, predominant source of fusion fuels that we use in deuterium-tritium fusion, which are the heavy forms of hydrogen, is that 20% of the fusion power, namely in the kinetic energy of the particles which are released, this is in a charged particle which is contained within the plasma fuel. And because the plasma fuel itself has all the particles have electric charge, so does this helium particle because it's a helium nucleus, and it has charge as well too. And therefore, by classic, you can go look it up, Coulomb collisions, which just means collisions between charged particles. This particle is forced to give its heat, basically its energy, back in the form of heat into the background fuel. Because it's on the order of like 500 times more energetic than anything else around it. So it basically zips off, collides with many things, slows back down to a meager 10 million degrees or 100 million degrees. And so why is this important? Well, so what this says is that if that's 20% of the energy, then when the energy gain gets past 5, this means after this point, it becomes much more like a star. It's because the heating, which is going into the fuel, is coming from its own reactions. And so from a science point of view, this is an extraordinary threshold to get over. So once you get above a gain of around 5, the plasma becomes much more self-determined. The fuel becomes much more self-determined. There's nothing plugged into the sun, right? It's in fact, it's what we call ignited, which means that there's zero external input actually of power into this. So we've never seen this condition in a controlled way ever on the planet Earth. Like that's an amazing science threshold to get over. And it's in fact the science pursuit of our own device SPARC, also of the ITER project, which is in the south of France. And everyone has agreed over and over again that that's the key next threshold to get over scientifically. Having said that, then it's also it's highly satisfying that that's the obvious next commercial goal as well too. What I mean by that is that if you don't have high energy gain out of the plasma, there's no point designing a power plant, because you can't just be sucking electrical energy into the plant and releasing less than this out onto it. And even though it varies a little bit then depending on the specifics of the technology, it almost for sure you must get above 5 actually to provide net electricity gain actually onto the system. It's what Professor Chapman was discussing yesterday about the tiers that we have to move forward. So that's the next threshold, and we hope that that's coming in the next few years, in fact, with the SPARC project. But there's other projects which are hoping to achieve that as well too. There's one that was just recently announced in China that's trying to achieve that goal as well too, and there's other efforts in the private sector as well too. So if it was again a comment to young students looking at this and trying to think about like what would be exciting careers, it's not just limited anymore to thinking about a government-sponsored laboratory and going forward with a career that looks like that, or become a professor at a university, which has been a wonderful career. I'm not going to complain about that at all. But there's actually a broader set of options actually on the table, particularly because of the advent of private sector fusion companies. And if one of those succeeds and we move forward to commercial fusion energy, it's hard to imagine this is going to change everything.
So what does collaboration look like between all these different sectors, private and public, and universities and different countries?
So fusion has an interesting story here. In fact, its origins were right all the way back to the 1950s, in the heart of the Cold War, which none of you guys remember. But it's because the Soviet Union and particularly Soviet Union, United States, and also the UK as well too had very major programs thinking, we basically figured out fission, nuclear fission, in a very short period of time. It's like, well, the next step is fusion, and this should be, we'll do this in the next few years or something like that. And there was efforts in the Soviet Union, the United States, here in the UK. Most of them were classified, and it was like it became apparent after half a decade of trying. It's like, oh my God, this is way more complicated than we thought it was going to be. We're not even close to actually reaching the conditions which are necessary. And it was interesting, it was declassified in the late 1950s, and it was one of the rare areas that actually the West and the traditional West and the Soviet Union actually collaborated scientifically. Yes. And in fact, it goes to there's a great story, just so you know like the tokamak itself. As I said, it was a Russian acronym because it was invented by two very famous Soviet-era scientists, Tam and Sakharov. And Sakharov ended up winning the Nobel Peace Prize actually as well too. So they executed on that idea, tried it out, brilliant idea, like no computers, just in their head, incredible scientists. And then they claimed that everyone was sort of stuck at really low temperatures in all the configurations they were trying. There were a few missteps. There was actually an announcement here in I think in the late 50s, early 60s, that the UK scientists had actually cracked the problem, and they thought that they had achieved major amounts of fusion energy, and it turned out not to be that. It turned out to be another thing, and they kind of mistook the signals for it. It's pretty complicated. And then so everyone had these missteps, and it's not really happening. And then the Soviets announced that they had achieved 10 million degrees, which is the point where you start getting to what we call thermonuclear temperatures, because at this point, the temperature of the plasma is hot enough that you should start seeing some fusion reactivity, and no one in the West believed it. So it's a great story. There was a team led from the UK, from the UK, AA, the Cullum Laboratory, which is here in the UK, that took this other very new invention called a laser, which is pretty also interesting that was the new invention, and the Soviets didn't have access to a laser, and they took it to the Soviet Union and they made an independent verification that in fact it was as hot as the Soviets had claimed, and that was the tokamak. And so after that, there was essentially an explosion of tokamaks being built in multiple places here in the UK, including at MIT as well too. So we built 3 tokamaks on the campus of MIT using very high field copper magnets. And SPARC is like the next generation of that, except it's even going up another level in terms of its size and the strength of its magnetic field. So it's an amazing story, in fact, of collaboration throughout that. And based on that, throughout the development of fusion, it's one of the other great things. It's been truly an international effort about advancing actually this fairly complicated science of fusion. Now we're in a slightly different era because, and I would argue this is very exciting. The fact that we've got private sector coming in means it is still generally open research, but it's a different flavor of this. And this has to do with the fact that the private companies have to protect their intellectual property around the inventions that they make. This is including our own spin-out company as well too that we have there. But we'll navigate this for something as important as fusion. We'll navigate this, and in the end, in fact, I was just looking at the paper that we published about SPARC, which is our own tokamak, and the physics design of the device is completely open. So it's in something called the Journal of Plasma Physics. We made it online available to everyone in the world. Last time I looked, it had like 20,000 downloads. You can go look it up. It's like an overview of the SPARC physics basis. And there was something like, besides ourselves and our own company, Commonwealth Fusion Systems, there were like about 10 other institutions represented on that paper. So that gives you an indication of, in fact, the multi-organizational aspect. And I think what we have to keep doing, which is working together, because fusion's still hard. Yes. Despite these successes. Yeah.
Is there anything that's holding that collaboration back in terms of politics or anything? I know Ian Chapman mentioned yesterday that we should treat the development of fusion technology as we did the development of the COVID vaccine. Is there anything that still needs to change, or are you happy with where that stands?
Oh, I mean, it's evolving. There's usually a general frustration with the pace at which governments, respond to these things. But it's important that we get it right as well too. But I think some more urgency across the board is needed on these things. And it's also multinational as well too. So as I mentioned yesterday, there's a very aggressive program for developing fusion energy in China. And that's in a very different development model and about what that would look like and how they would deploy that. Now, I would just argue it's, so in some sense, I laud that effort because it's good that we have multiple things trying to make fusion work. But it's also an indicator it's going to have pretty significant geopolitical impact about who develops and deploys fusion first as well too. So I really have to, I would say the leader, I would state the leader in this is the UK actually. Yes. The UK has a very much, presided over by Professor Chapman as the head of the UK Fusion Program, but has really gained deep political support in the UK for understanding that a place like the UK with its, pretty deep bench in terms of technology and science, but also with a really well coordinated plan and its long history in this field, could really leverage these things into having a leadership role going forward. So that's fantastic. Like I actually tell the US government, you need to be looking at the UK for leadership actually in this area, because they've adapted themselves in thinking about all the things that you need to do, which is namely figure out how you couple into the very important aspects of the commercialization of fusion, but also still simultaneously do the things the government aspects, the public aspect must do, which is around, I think, supporting training of young scientists and then still, following the curiosity-based R&D as well too. All these things are still necessary parts of it.
And you're clearly a leader yourself as well in your own right. Do you have any advice for leadership as a skill, or how you'd go about leading a project or a team?
Oh, that's a good question. So one of I mean, it was interesting in our own experience of me being at MIT, and I think this hopefully helps a younger audience for this podcast as well too. Was one of the most important things that I did was I trusted the talent and the drive actually of young people. So SPARC was a project. So you look and go, oh look, he's the director of the Plasma Science and Fusion Center, and he was and he led this program going forward. Well, the reality was like there were six of us who were basically the co-founders of the company and actually figured out this thing. You ask about the structure and the coordination of this. Like we hammered this out about what this would look like to have a leading university like MIT and a company work together to actually solve the problems. But 4 of those, when we did this, were students and postdocs. And in fact, the postdocs and the students mostly went into the company. And then I stayed behind at MIT to be the director of what was the largest research sponsor for the company as they try to get over the hurdle of this. So what I would say is be making sure that you're not just thinking about innovating in a technical way and in a scientific way, which is a really important part of leadership. You also must innovate in an organizational way as well too. And so what I mean by this is be thinking about different. Sorry about that, universe. Is thinking about unique ways at which you can access and deploy talent. And in the end, it was really important that we. I was commenting. I didn't even know what this meant actually, but that somebody said that we had a very flat organization. And so to me, this means that it's merit-driven rather than sort of hierarchy-driven. And there has to be hierarchy in all kinds of organizations. But that was probably the most important thing that I did, actually, was trust young people. Yeah.
Yeah, that's really interesting. So one final question for the audience out there. What one piece of advice would you give to your 18-year-old self today?
I know this is a good question. No, because I give this advice to my own to my own daughters. It's really important to study hard and to work hard, but also make sure you're enjoying your youth as well too. My advice in general about people who are at that stage is kind of own your trajectory. And what I mean by this is that all of the cases that I've seen of the most successful people, and what I mean by success is not necessarily monetary success or even that you gain a particular position, but it's clear that you found your way to a place where you're really fulfilled by what you do. And it's like, I would argue, I got there because I'm very fulfilled by what I do, both about it satisfies me personally as to the things that I love about doing science and doing discovery, but also hopefully about being impactful and also about working honestly with young people, because in the end that actually turned out to be something that it really satisfies me. So the only way that you know how to do that is by going out and experiencing those different things. And so the most successful people, own their education. They own their career trajectory. Like, don't wait around for somebody to tell you this is what you should do or this is the thing that makes you satisfied. Go explore those things. Figure out what it is. If it's something like coming into research or working in new energy because you're motivated by that and it fulfills you, then Godspeed, right? But don't let somebody else tell you what to do. Listen to advice, but listen to your heart as well too.
Thank you so much for your time. That was really fascinating.
Thank you, Casper. Really appreciate it. Thanks. Okay.
Brilliant.
Thanks.
Thank you. Having spoken to Professor Whyte, it's clear to see why he's a 2-time winner of the Ruth and Joel Spira Award for Distinguished Teaching from the School of Engineering at MIT. What a great role model. Understanding how close we are to making fusion energy a commercial reality is inspiring, and I, for one, will certainly be following his work and the work of his team. 2025 is going to be an exciting year, I'm sure. Thank you for listening. Until next time, and please like, subscribe, and share with your friends.